Hi, we're going to be looking at combining functions today. But before we do that, we need to figure out where we can evaluate these functions and have a valid input. So when you're looking at functions, there are essentially three things at this point in the course that we're going to wonder about for the domain. So these are sort of the three rules where we're going to eliminate the domain. So number one, we can't have a zero in the denominator. Of course, we can't divide by zero because that's not allowed with real numbers. So we're looking for x values that have a zero denominator, and we're going to weed those out of the domain. The second thing is we can't have a negative value under an even root. Again, this is true because if we know that if we have like the square root of -4, we would have an imaginary number like 2i, or the fourth root of a negative number. We can't find a real number that we can multiply together 4 times that's going to give us a negative number. It just doesn't work. So those won't be real numbers. Finally, and we'll have some more restrictions later, but finally, it has to make sense in the context of the word problem, in the context of a word problem. So if we are working through a problem that says, let's find the time it takes to make so many units of something, and we get a negative time, that's just not going to work. So we'll have to weed that out. So when we're working with functions, the first thing we need to do is find their domain. I have three examples here. Let's look at f of x first. So I want to find the domain of this function. Notice that right here we do have an x value that's in the denominator. So we know that when x is equal to 4, that denominator is going to be 0 and we need to weed it out. So what I usually do is I say, okay, if I have an x in the denominator, I'm going to say that x minus 4 has to be or can't be equal to 0. I solve for x, so x can't be 4. What that tells me is I can have anything for my domain from -infinity to 4 union 4 to infinity. So it's just that one singular point that I have to take out. Can't put 4 into this function. The second one, notice that we have a square root. So we can't have a negative value under an even root. And the square root is an even root, so what I'm going to do is say x plus 5 has to be greater than or equal to 0. I can take the square root of 0. It's, of course, 0, so I can do that. If I solve this inequality, I subtract 5 from both sides. So I have x is greater than -5 or equal to -5. So my domain is going to be -5 to infinity. So anything greater than or equal to -5, I can include that. That's in my domain. Anything less than that is going to make this an imaginary number. Okay, and finally, I have x plus 4 squared minus 3. We know that is a parabola that's been shifted to the left 4 and down 3. So we don't have any denominators here in this quadratic. We don't have any roots. It's not in the context of a word problem. So we should know that we can put any number into a parabola and get an output. So here we have all real numbers, or if you would want to put it in interval notation, we'll say -infinity to infinity. So before we talk about combining functions, we want to talk about their domain. So now in the context of combining functions, we can actually do that. So let's say, for instance, we want to find if f of x is equal to this function x plus 4 squared, and g of x is equal to 3. So we have a parabola that's been shifted to the left 4. We have a horizontal line at y is equal to 3. We can actually combine a new function by adding and subtracting, multiplying, dividing, taking compositions of these. The first thing we're going to do is we're going to go ahead and evaluate f at 2. So we're looking at evaluating functions at points. I go to my f function here, and f of 2 says wherever I see an x, I'm going to plug in the value of 2. So let me see if I can illustrate this with color. So f of 2 means I'm going to go to that f function, and whenever I see an x, I'm going to plug in 2. There we go. So I have parentheses 2 plus 4 squared. Let's do what's in parentheses first. Square it, we get 36. So we just get a value for a function out. So this is a little bit of review, right? Let's look at g of 2. So we go to our g function, and wherever there's an x, I put in 2. Well, the g function with this horizontal line, we always get 3 back. So g of 2 is going to be 3. In fact, g of anything is going to be 3 here. So if I wanted to find, let's say, the difference of f and g at 2, we could use this notation. So f of 2 minus g of 2 is the same as f minus g of 2. That's how you say that. So f minus g of 2 is going to be f of 2, which we said was 36, minus g of 2, which is 3. And so we'll get 33. Now we can talk about putting those functions together and making new functions. So let's see what f minus g of x is. So f minus g of x is the same as f of x minus g of x. So we're going to have this x plus 4 squared, f of x, minus the g of x minus 3. So we can create new functions by combining functions. In this case, we're doing subtraction. And notice that that's going to be the same function as c up here by combining those two functions together. When we're looking at combining functions, we have this notation here. So we have f plus g of x. We can simplify that as saying f of x plus g of x. And the domain of this is just going to be the domain of each one of those functions have in common. This is f minus g of x, just what we did up there. So that's going to be equal to f of x minus g of x, and the domain is going to be the intersection of a and b. Notice up here, the domain of x plus 4 squared is going to be all real numbers, and same with the domain of g of x, which is equal to 3. When you intersect those, take what they have in common, we get that new function, which still has all real numbers as its domain. F times g of x, we can simplify that into f of x times g of x, and the domain is going to be what they have in common. Finally, f divided by g of x, we'll rewrite that as f of x over g of x, and this is going to be defined at all real numbers in the domain of both, just like the other ones, except where that denominator is 0. So where the denominator is 0 would be where that g of x is equal to 0. So we're going to weed out this part, and that's what this says here. I know it's some complicated notation, but it says the domain will be the domain of f intersect the domain of g, such that, that's what this line means, such that g of x is not equal to 0. We're going to be looking at example of this and some others below in just a minute. Okay, let's take a look at putting some of these functions together by combining them. We're going to be looking at two linear functions, f and g. We're going to first start again with f minus g of x. what I would do first is just write down the rule for that. So f minus g of x is the same as f of x minus g of x. Now I'm just going to plug those functions in. I have 2x plus 1 minus parentheses 3x minus 1. It's important to have parentheses here because I'm going to distribute that negative through. Sometimes students miss that. So that's why I put both of these in parentheses, just to remind me. I'm going to clear those parentheses, so I have 2x plus 1. I'm going to drag this minus through, so I'll have minus 3x minus a minus, so plus 1. That's the tricky part. And now finally I can combine these together. 2x minus 3x is negative x, and 1 plus 1 is 2. So combining these functions by subtraction, we get negative x plus 2 as a new function. This is asking for the product. So I have f of g of x, f times g of x. I'm going to write that as f of x times g of x. And I can use a dot here or just juxtapose those together. That's going to be 2x plus 1 times 3x minus 1. And I'm going to go ahead and distribute through. So I'll distribute through the 2x. I'll have 6x squared minus 2x. And then I'll distribute the 1 through. So I'll have plus 3x minus 1. And notice how I put those together in terms of one grouping and two, so I can just add those together. You can do it how you'd like. I just think that this is sort of a neat little way to do it. So I have 6x squared plus x minus 1 when I simplify those out. Okay, finally I have division. Notice in the first two, of course, the domains of these are all real numbers, and what we get are domains with all real numbers. The last one, we have f of x divided by g of x, and that's going to give us 2x plus 1 all over 3x minus 1. Here is my new function. Well, we do know that we have an x value where it's undefined. We're going to take a look at that right now in example 4. So example 4 has us finding f divided by g of x, where we have a quadratic for f, and we have a linear function for g. We're going to see what happens at the value x is equal to negative 6. We're going to evaluate that new function at negative 6. So the numerator is going to be 3. Again, I can use different color if I want to. I'm going to plug in negative 6 for every x value here. So 3 times negative 6 squared plus 4 times negative 6 minus 4. I'll square negative 6. Negative 6 times negative 6 is 36. Minus 24 minus 4. I'll multiply those two together. I'll have 108 minus 24 minus 4. That's minus 28. That would give me minus or plus 80. Plus 80. That's going to be my numerator here when I evaluate at 6, negative 6. G of negative 6, my function for g is x minus 6, so I'll have negative 6 plus 6, and of course that's going to be 0. So when I put these together and try to evaluate that new function f over g of negative 6, I would get 80 over 0, but I can't divide by 0, so this is undefined. Again, what I'm doing is sort of verifying this domain rule up here. So when I'm taking the division of two functions, I have to take the domain of what they have in common, but I need to weed out any points where g of x is equal to 0. So we can see that the domain of this function is going to be negative infinity to negative 6 union negative 6 to infinity, because negative 6 is going to be the only point where g of x is equal to 0. So therefore, f divided by g of x is equal to that division unless that denominator is 0. Hopefully that drives home the point with that division. Now, in a minute here, we're going to take a look at composition. It's possible by this point that you've seen those other combinations of functions, and even if you haven't, they're fairly easy to grasp. Composition of functions will probably be a new one for you, though. Composition is very important in mathematics because it actually takes two processes and puts them together in a certain way to make a new process. So a composite function takes the um, it takes the output of the first performed function and uses it as the input for the second performed function. So it's going to take the output of what we do first here and use that as an input for f. The domain is a little more complicated here. So the domain of a composition of functions is actually going to be the domain of our answer, but we have to take it intersected with the domain of that function we're putting in. So what that means is we're going to have to make sure that what g of x is going to be defined for f, and then we take what's in common with that and the whole composition. Let's take a look at an example of this composition down here. So in example 5, we're given two functions, a square root function and a linear function. We want to find the following and give the domain of those general compositions here. Let me go ahead and zoom in a little bit so we can see that notation. When we have a composition, this is f of g of 4, we always rewrite it. So this is going to be f of g of 4. So we use for that we use parentheses here. What I like to do is I like to always evaluate g of 4 first. So I have f of, I'm going to my g function here, and wherever I see an x, I'm going to put in 4. I'm going to try to use color here again. So I have 2 times 4 plus 1. So I'm going to take the output of that. The output of g of 4 is going to be 2 times 4, 8 plus 1 of 9. And I'm going to use that as the input for that second performed function, f. So now I go up to my f function, I take that output, 9, and plug it in wherever I see an x. This gives me the square root of 9, which is 3. That's evaluating the composition at one point. Okay, now let's do the other way. So what if I wanted to do g of f of 4? I would rewrite it, g of f of 4, just like this. I'm going to start by computing f of 4. I go to my f function. Wherever I see x, I'm going to plug in 4. So I have g of the square root of 4. We take the output of that square root, which is 2. That gives us g of 2, because the square root of 4 is 2. And then we go to the g function. This time the g is our outside function, and we plug in 2 wherever we see x. That'll give us 2 times 2 plus 1. That's 4 plus 1, or 5. So here I want to drive home the point with this example is that we're just evaluating these functions at a point, the compositions at a point, but f of g is generally not the same as g of f. When it is, we're going to have a special relationship, which we'll see in the next section, actually. So now we're going to find what those functions look like in general, so I could plug in anything. When I have a general function like this, I have f of g of x. I'm going to rewrite it again. Now remember, when I do this, what I'm going to get is a new function. It's going to be a function. So I'm going to do f of g of x is 2x plus 1. Now I'm going to go to my f function, and wherever I see an x, I'm going to plug in that 2x plus 1. So I'm going to have the square root of 2x plus 1. That's going to be my new function. So when I take the composition of a square root and a linear function, I get that square root of that linear function. I'm trying to find the domain. If you remember from our conversation with the domain, we need to figure out where we have a denominator of 0, no denominators here, where we have negative under a square root. So when we're looking for the domain, that 2x plus 1 has to be greater than or equal to 0. Otherwise, we're going to get an imaginary number. So I'll have 2x is greater than or equal to -1. I'll have x is greater than or equal to -1/2. That's the domain of the new function. But remember, with composition, I have to intersect that with the domain of my input. The domain of my input is going to be all real numbers because it's just linear. So what that means is what I have in common with all real numbers and x is greater than -1/2 is just that x is greater than or equal to -1/2. So my domain is going to be -1/2 to infinity. I include the -1/2 and I go all the way out. So I can evaluate f of g of 4 or f of g of 0, but I can't evaluate f of g of -pi or -2 because that's going to be out of our domain. Let's try to find a function rule for g of f of x. First, I rewrite. Second, I go ahead and substitute for that f of x. That's going to be my square root function. So I go to my g function, wherever I see an x, I'm going to plug in that square root. So I have 2 times, there's an x, so I have the square root of x plus 1. That's my new function. When I'm trying to find the domain, I notice that my new function has a square root. It has to be positive or at least 0 in there. So x, what's under the square root, has to be greater than or equal to 0. But also, when I look at the inside function, I have to take the intersection with that. Our inside function also says x has to be greater than or equal to 0. So when I take what's in common with both of those, I'll get for both of those that, x has to be greater than or equal to 0. So that'll be my domain for this one. What it's saying is for this function, I can plug in 0 to infinity. Anything positive or 0, nothing negative. Finally, at the end of this section, I have a reminder and then 2 practice problems that you can work with. So usually, f of g of x is not equal to g of f of x. When it is, we have a special function, and we'll see that in our next section. So I have 2 more for you to take a look at. I'm going to do these quickly, see if you can get the same thing. F of x minus g of x. Plug in those functions, 2x minus 1 minus x squared plus x minus 2. Be sure to distribute, right? So 2x minus 1 minus x squared minus x plus 2. Distribute that minus through all 3 terms and then combine like terms. I'm going to say minus x squared. 2x minus x is just x. -1 plus 2 is 1. That's another difference. F times g of x, I'm going to go ahead and multiply these again. So I write f of x times g of x. that's going to be the same as 2x minus 1 times x squared plus x minus 2. I'm going to distribute through. Distribute the 2x into each one of these terms. I'll get 2x cubed plus 2x squared minus 4x. Now the negative 1. And you might remember how I do this. So negative 1 x squared, I'll put that right under my x squared term, negative x and plus 2. I add those together, so I get 2x cubed plus x squared minus 5x plus 2. So there you go. There's a good example of a lot of combinations of functions. Again, we'll be using these later on in the course to make new functions with the ones we know. Thank you.